When we hear the word radiation, it's tempting to picture huge explosions and frightening mutations. But that's not the full story. Radiation also applies to rainbows and a doctor examining an X-ray. So what is radiation really, and how much should we worry about its effects? The answer begins with understanding that the word radiation describes two very different scientific phenomena: electromagnetic radiation and nuclear radiation. Electromagnetic radiation is pure energy consisting of interacting electrical and magnetic waves oscillating through space. As these waves oscillate faster, they scale up in energy. At the lower end of the spectrum, there's radio, infrared, and visible light. At the higher end are ultraviolet, X-ray, and gamma rays. Modern society is shaped by sending and detecting electromagnetic radiation. We might download an email to our phone via radio waves to open an image of an X-ray print, which we can see because our screen emits visible light. Nuclear radiation, on the other hand, originates in the atomic nucleus, where protons repel each other due to their mutually positive charges. A phenomenon known as the strong nuclear force struggles to overcome this repulsion and keep the nucleus intact. However, some combinations of protons and neutrons, known as isotopes, remain unstable or radioactive. They will randomly eject matter and/or energy known as nuclear radiation to achieve greater stability. Nuclear radiation comes from natural sources like radon, a gas which seeps up from the ground. We also refine naturally occurring radioactive ores to fuel nuclear power plants. Even bananas contain trace amounts of a radioactive potassium isotope. So if we live in a world of radiation, how can we escape its dangerous effects? To start, not all radiation is hazardous. Radiation becomes risky when it rips atoms' electrons away upon impact, a process that can damage DNA. This is known as ionizing radiation, because an atom that has lost or gained electrons is called an ion. All nuclear radiation is ionizing, while only the highest energy electromagnetic radiation is. That includes gamma rays, X-rays, and the high energy end of ultraviolet. That's why, as an extra precaution during X-rays, doctors shield body parts they don't need to examine, and why beachgoers use sunscreen. In comparison, cell phones and microwaves operate at the lower end of the spectrum, so there is no risk of ionizing radiation from their use. The biggest health risk occurs when lots of ionizing radiation hits us in a short time period, also known as an acute exposure. Acute exposures overwhelm the body's natural ability to repair the damage. This can trigger cancers, cellular dysfunction, and potentially even death. Fortunately, acute exposures are rare, but we are exposed daily to lower levels of ionizing radiation from both natural and man-made sources. Scientists have a harder time quantifying these risks. Your body often repairs damage from small amounts of ionizing radiation, and if it can't, the results of damage may not manifest for a decade or more. One way scientists compare ionizing radiation exposure is a unit called the sievert. An acute exposure to 1 sievert will probably cause nausea within hours, and 4 sieverts could be fatal. However, our normal daily exposures are far lower. The average person receives 6.2 millisieverts of radiation from all sources annually, around a third due to radon. At only 5 microsieverts each, you'd need to get more than 1,200 dental X-rays to rack up your annual dosage. And remember that banana? If you could absorb all the banana's radiation, you'd need around 170 a day to hit your annual dosage. We live in a world of radiation. However, much of that radiation is non-ionizing. For the remainder that is ionizing, our exposures are usually low, and choices like getting your home tested for radon and wearing sunscreen can help reduce the associated health risks. Marie Curie, one of the early radiation pioneers, summed up the challenge as follows: "Nothing in life is to be feared. It is only to be understood. Now is the time to understand more so that we may fear less."
Radiation. Radiation. We are all scared of radiation. All of us, really. I mean, and we are all exposed to radiation, but nevertheless, we are all scared of radiation. Now, if you are scared of radiation on Earth, be prepared. You will be much more scared if you go in space flight. To the point that the question of this talk will be, is this a showstopper? Should we just forget about space because radiation is too high? Well, how much radiation we have in space? And you have seen this already. This is Curiosity. And Curiosity, the MSL, the Mars Science Lab, made the first measurement of radiation in space during the transit to Mars and on the Mars surface. So now we know how much radiation we have in space. How much is it? So how much is on Earth? You know, on Earth is this little square down here. We measure the radiation in millisievert. Now it's a strange unit, but basically all of us, we receive 1 millisievert per year. So in 1 year, we get 1 millisievert from everything, from the environment, from the soil, from the food, from the cosmic rays. And then it really depends on how you live. I mean, if you go to the dentist many times, as I do, you get a lot of X-rays, and then you have more dose. If you travel a lot, you even get more dose. If you are married, if you sleep with another person, we are all radioactive. So if you sleep, this person sleeping next to you for at least 8 hours per day, some of my friends, 16 hours per day. They get irradiated by the other person, you know, and that's something people should know before you get married. You should sign an informed consent, I say. Just a warning. But now if you're worried about that, you can say, okay, but you want to go to Mars. Keep in mind that on Mars, you have 200 millisievert per year. So you can sleep with another person. I mean, it's not such a big deal. Because, you know, on Mars, it's almost like 1 year on Earth. So it's much higher. And even worse, if you are in deep space, you don't have the protection of the Mars atmosphere, you don't have the protection of the planet itself, so you have 700 millisievert per year. So 700 millisievert per year in deep space as compared to 1 millisievert per year on Earth. Clearly, a very much higher dose. Is this dangerous? Is this a showstopper? The problem is not only the quantity that you get more radiation. The problem is the quality. It's different radiation. We know radiation on Earth. We know X-rays, gamma rays, beta rays, we all know. But radiation in space is heavy ions, iron, these exotic particles, very heavy, very densely ionizing. We say this is a beautiful image that you see. What you see here, this one, is a human cell. This is a human nucleus. You know, it's 10 microns approximately. And these two lines that you see here are two iron ions that you don't find in space. I'm sorry, that you find in space, but not on Earth, except in Darmstadt, the GSI, where we have it, going through the cells and making damage to the DNA. What do we know about this radiation? We really don't know much, because we don't know it on Earth. We only know it in space, or if you are exposed to GSI by accident, which never happened. So the only thing we know, we really know, it comes from the comics. You know this guy. This is the Incredible Hulk. The Incredible Hulk, he was actually exposed to gamma rays. I think you remember the story. He was working in a nuclear power plant, and then he got exposed to gamma rays, and then he becomes very nervous and green and very aggressive. So this is radiation on Earth, typical effect of radiation on Earth. Now, if you go to space, this is what is going to happen. These are the Fantastic Four. You know, I was a kid, I thought this was fascinating, because one becomes like a stone. I mean, and she's my favorite. She becomes like invisible at will, which is very convenient. This becomes like a fire. I mean, when I was young, I wanted to work always on radiation because I thought that could become, invisible at will. It doesn't work that way. So don't try it at home, please. But it's not all crazy. Hulk gets nervous, and we know that radiation has some effects on the brain. So you can actually, it's not impossible. And this story that you get the same dose, I don't know if you remember, the Fantastic Four were on space, and then they get exposed to radiation. They are very different, but this is what we call inter-individual variability. In the clinics, in radiotherapy, people know that if you irradiate 4 patients, you will get 4 different responses. I mean, not so different, but still kind of different. So what do we know apart from that? The other thing we know is that radiation on Earth is done of photons, electrons. These are small particles. And radiation in space, you see, is these heavy particles. So what do you expect? You expect something like that. This is our little astronaut on Earth. And he's getting energy. The millisievert is really energy from these lentils, I believe. So you make some damage, but he's still kind of standing. Now, if he goes to space, the same energy, that's what is going to happen. Now you have heavy ions, and you have less peas than lentils, same energy, but the effect is clearly different. So that's what we try to understand. We try to understand what is the qualitative difference. But can we protect ourselves from radiation? Well, this is, I want to point out as my previous speaker that this is not a girl playing with the sand. This is a serious scientific experiment. It's a serious scientific experiment where this researcher at GSI is trying to measure the shielding properties of the Mars soil. Here it is for you. This is Mars soil. Not really. It's a simulation of the Mars soil, but really looks like the Mars soil. I mean, it's identical. It's pretty much the same. So, I mean, if you want some, I can sell it for a reasonable price. We even have moon. This is moon soil, which is gray. And actually, this is also showed by the previous speakers. You have these nice caves. So you can go on Mars, you can go in the caves, and you will be protected with this very thick shield. You can even do, this is Mars concrete. These are bricks that you can do with the Mars soil. It's better to use the caves than to dig, because if you go to a construction site here in Germany, you see that when people are digging, they make a lot of dust. So you can imagine on the moon, where the gravity is 1/6, you really make a lot of dust. So you don't want to be digging. But this can be effective if you are on the planet. What about during the transit, when the dose is even higher? You cannot bring heavy shields, because, the weight is what is really expensive in a spacecraft. So you don't want to bring heavy shield. Shielding is a very nice solution on Earth when you go to the dentist. Again, not my dentist, but your dentist. Don't go to my dentist, because he uses a lot of X-rays and no shielding. Now, your dentist uses not so much X-rays and plenty of shielding, but that's heavy, so it's a big you will not solve the problem using passive shielding. You can think of active shielding. You can think of electrostatic shielding. I mean, some kind of electrostatic spheres that protect the astronauts. Or even better, you can think to this thing. This is shielding. This is something I think all of you know. This is a beautiful aurora borealis. What is this? This is the shielding of the Earth, the magnetic shielding of the Earth. The solar wind, with these protons and heavy ions, is coming to the Earth, is trying to enter in the Earth, but the magnetic field of the Earth is deflecting these particles. They go to the poles, and then they hit the atmosphere, and you see these beautiful colors. Beautiful. There are many people going there only to see them. You see that the green colors is the oxygen. Sometimes it's more on the red than is nitrogen. So that's how Earth is protecting life, using a magnetic field. So we could think about using the same system. It's not so easy, but it can be done. So what do we do really at GSI? We simulate the cosmic rays. This is this is our accelerator at GSI. We also have many people, 1,000 people working there. We also have lawyers too, not scientists, but also lawyers, mostly scientists. And we can simulate the particle. We need these huge accelerators because the cosmic rays are so energetic. They are so fast. So you need a very large and expensive accelerator to simulate space radiation. But there is a nice part of the story. I told you these particles are so effective. You do remember the little astronauts killed by the cosmic radiation, which is bad if you are in space. But if you are a patient, and if you can take these same particles and you can shoot them in the tumor, not whole body, but only in the tumor, then you can cure cancer. Well, this is done. And not very far away from here. It was done in Darmstadt for many years. Now it's done in Heidelberg. This is a picture of a treatment room in Heidelberg. But they are treating the patients using heavy ions, using carbon ions in this case. So I think this is really fascinating, is the possibility that space research and medicine help each other. You know, that the same radiation which is a problem in space can be a cure for cancer on Earth. So at the end, shall we go to Mars or not? Well, I think I was supposed to give ideas here. It looks like, I mean, radiation is a problem. This is clear. Shielding, passive shielding can be a solution on the planet, but not really on transit. Maybe the best solution, the best idea is to use a magnetic shielding, is to build magnetic fields for the spacecrafts that can do what is done on Earth. So it's not really a new idea. It's the same idea that God had a few billions of years ago when he said, okay, I want to make life, but I created radiation already. What can I do now? Okay, maybe I can make a magnetic field, you know? And you see, it's very effective in protecting the Earth and our life from space radiation. Thank you very much.
Ladies and gentlemen, it's a great pleasure to be here today. And today I will take you for a trip from Antarctica to the Moon and then to Mars. Last winter, I went to Antarctica, to the Belgian station that you can see here located on this map with the Belgian flag. I'm a biologist and I'm working at the Belgian Nuclear Research Center. And space and Antarctica have a lot in common. Both are considered as extreme environments, environments where it's difficult for mankind to survive. Let's look at the weather conditions in Antarctica, for example. You can have wind that blows up to 240 kilometers an hour, temperature up to minus 90 degrees. You can easily understand that people, the crew in Antarctic stations, can be isolated, confined for days and weeks and months in a row, like in space. Antarctica is one of the very best analogs, simulators of human space exploration to Mars. Here, that's me, in Antarctica, on the beautiful Belgian Princess Elisabeth Station, located 200 kilometers from the coast. The Belgian station is the only zero-emission station in Antarctica. where energy, electricity, is produced through 9 wind turbines and 200 solar panels. And I was very lucky to be able to go there and to perform studies on human health and to precisely monitor how human health changes little by little, days after days, during a stay in Antarctica. And through these studies and the samplings that we have been performing, biological samplings on blood, urine, heart monitoring, saliva, we can monitor millions of parameters in order to really subtly understand the changes in the human body. Antarctica is just the very first step to understand what happens when a person, an astronaut, is confined for a very long time in an isolated environment. But we are living in a very exciting period of time where international space stations and space agencies are really gathering together and for the same kind of quest, and they are all aligned in order to go first around the moon, then on the moon itself, and then further away to Mars and maybe later on to Saturn or Jupiter. And this is what we call the Deep Space Gateway Program. This will be the human first spaceship to go to recognize the solar system and to go deep in space. But there is a big concern and a very big issue, and this issue is ionizing radiation, space radiation. Ionizing radiation are types of radiation that can ionize the matter. They can ionize molecules inside the matter and inside our cells, inside our bodies. We don't realize how much here on Earth we are really cocooned. We are surrounded with an atmosphere, and this atmosphere protects us from space radiation and from ionizing radiation, like a layer of 1 meter of metal. And furthermore, we have our Earth magnetic field that stops about 99.9% of space radiations. So we are really cocooned. Radiation has been always present since the birth of the universe. The Earth is radioactive. We are naturally radioactive. What we eat is naturally radioactive. The plants, the animals, the bacteria are radioactive. But it's not harmful. These doses of radiation are extremely low, and life has evolved with this ever-presence of very low level of radiation on Earth. But let's move, let's quit the Earth, and let's see what happens on the International Space Station, for example, at 300, 400 kilometers in orbit around the Earth. What do we have there? Our physicists from the Belgian Nuclear Research Center have measured and characterized radiation inside the ISS. And they estimated that the dose of radiation is about 150 times higher than on Earth. They placed radiation detectors inside the ISS and also outside the ISS, whilst we, the biologists, are measuring the impact of this cosmic radiation on the health of the astronauts. And we get samples from these astronauts before they go to space, and then 6 months to 1 year later when they come back from their trip to the International Space Station. And we measure how their cells can repair DNA damage induced by space radiation. And we see that each astronaut has got a different individual susceptibility towards radiation, a different radiation tolerance. And whilst our microbiologists are also preparing flight to Mars inside the International Space Station, and earlier this year we flew the first bioreactor containing a bacteria called Spirulina atrospira. And this atrospira is a beautiful cyanobacteria that can use photosynthesis, that can perform photosynthesis, it can produce oxygen as well as food. So our microbiologists are working on different ways of using bacteria in order to recycle organic matters, purify urine, produce oxygen, and produce food. And this is what we call the MELISA loop, and this is a very important program from the European Space Agencies. Later on, when we will go to the moon, we leave from the ISS, 300 kilometers from Earth, to the moon, 380,000 kilometers from here. There will be no magnetic field. There will be no atmosphere. So the dose of space radiation will be much higher. But the moon will be a very important step for us and for mankind in order to test and to be a springboard, testing board, in order to make sure that everything is going fine in order to go to Mars. And this is also where we will test different shielding material. How can we better protect mankind and the moon village that you can see from cosmic radiation? And thereafter, we'll go to Mars. This is then 225 million kilometers from Earth. Why do we want to go to Mars? Mars is the closest planet in our solar system, closest to the Earth. It's also the most similar to the Earth. It was warmer once there, and there was water. So it's important to see whether life has also existed there in order to understand how life started on Earth. But if we look at the dose of radiation, I mentioned on the ISS, you will have 150 times more radiation than on Earth. On the moon, 300, 400 times more radiation than on the Earth. On Mars, we'll have, for a trip to Mars and back, 1,000 times more radiation than on Earth. So it's very important to devote some energy and to perform research in order to understand how we can better protect our astronauts. But let me define the 3 types and categories of radiation and space radiation. First, we have the solar wind. The solar wind is not so harmful. It's a continuous flux of low-energy particles, and it can be stopped very easily by the spacecraft skin. However, sometimes we have solar particle events. These are storms of really high energetic particles, electrons and protons. This is an intermittent flux of radiation, but that can be deadly. And usually, the astronauts know a few minutes, a few hours before these storms are really coming towards the spacecraft in order to shield themselves, to go in a protected part of the spacecraft. And then we have the galactic cosmic rays. These galactic cosmic rays are a very big concern for us because we can't stop them very well. So far, all the technologies that we have developed and the shielding that we have found out and developed is not so efficient. And these galactic cosmic rays are high energetic particles like protons, like alpha particles, like heavy ions. And when they come and penetrate inside the spacecraft, they emit a myriad, a shower of secondary particles that will themselves irradiate much more. So it's very important to understand and to block them and to stop them if we want to go to Mars. When a cell is irradiated with radiation, ionizing radiation, you can see here on the left a normal cell on Earth, a cell which is stained with the nucleus appearing in blue. In the middle, you can see a cell irradiated with a high dose of irradiation in order to kill the cell, like in a radiotherapy treatment, when we want to kill cancer cells. And you see the spots inside the blue nucleus that corresponds to the location of the DNA damage. But when you see that when we irradiate with galactic cosmic rays, like iron ions, the damage, the spots are much higher, much more complex. There is much more damage for the cell to repair. And so there is a higher risk that the cell is going to misrepair, not repair completely and fully the DNA damage. And this is a very high risk thereafter to have an induction of diseases like cancer or other degenerative diseases. So for us scientists, it's very important to think outside the box and to develop ways in order to protect the best way we can astronauts in view of their trip to Mars, but also with a direct benefit on Earth. One of the first ways is to increase our shielding material, test different material properties in order to see what is the very best that protects the very best against galactic cosmic radiation. Another way is to select astronauts for the ones that are the most tolerant towards radiation. And this is what we see already in our studies on the ISS, that every astronaut has got a different radiation susceptibility. Like in our population, 5 to 10% of the people are really radiation resistant, whilst 5 to 10% are very sensitive. Understanding what are the parameters that makes this radiation sensitivity is crucial in order also to adapt radiotherapy treatment to even better cure from cancer. Another way is to develop and study powerful radioprotectors. These are pharmacological compounds, substances, medication that can really boost our system, our protective system, and really avoid cells to be damaged in a first instance. And we are studying at the Belgian Nuclear Research Center different powerful and very promising radiation protectors that can be also used for patients in order to protect the healthy tissue and to sensitize even more the tumor before radiotherapy. Another way is to genetically modify astronauts, to somehow modify the genes that are the most important and the most crucial, and that will allow these astronauts to repair very fast the DNA damage and to protect them very much against ionizing radiation. And for that, we have found out about 20 beautiful biomarkers that can very well determine the radiation susceptibility of an individual. Then hibernation. When animals during the winter are hibernating, their metabolism goes much lower. And the fact that their metabolism is slowing down, that increases their radiation tolerance, and they become more radiation resistant. So this could be also a way to boost the radiation resistance of our astronauts. And then on board, to go to Mars, it would be also very good to have the tissues of the astronauts, their cells, in order to regenerate them if needed, if an organ, if a tissue doesn't work very well anymore, to be able to reimplant this tissue, this new tissue working again very powerfully inside the astronauts. So I took you from Antarctica to the Moon and then to Mars. But Mars will not be the final destination, because mankind, through technological advances, through our scientific mind, will always want to make the impossible becoming possible. But before finishing, I would like to bring you back on Earth and tell you that space radiation research has got a tremendous benefit on Earth, and certainly for our cancer patients. If we can understand better the harmful biological effects of space radiation, like, for example, the protons, the heavy ions, the alpha particles, we can thereafter develop even better, targeted, precise, personalized therapies for our cancer patients. And this is extremely important also to develop new radiopharmaceuticals that will kill even better cancer cells. And this is important for our society, and this is also very important for the Belgian Nuclear Research Center to treat better diseases and to cure and save lives even more. And thank you very much, and I hope to see you on the Moon soon.
Привет! И спасибо за приглашение. Моего доклад прямо к Mars. My talk is Mars Direct, humans to the red planet within a decade. Now, how can that be? Many people have the preconception that human missions to Mars is something for the future, for the next generation or one beyond. Perhaps it is because they have seen concepts like this as the basis for such a mission. This is actually a NASA concept for a Mars spaceship. It looks like an Imperial Star Destroyer. Giant nuclear electric engines, ion drive. You can see it's quite large. Mars is there for scale. And, but this is not a design for a Mars mission. This is an attempt to realize the science fiction vision of the interplanetary spaceship. But what a Mars mission is about is not realizing giant spaceships. It's about sending packages, sending a package from the surface of the Earth to the surface of Mars, capable of supporting a small group of people, and sending either that or a comparable payload back. So what do we need to do that? Not this. We need this. Okay. Back to the future. You're looking at 1972, Saturn V taking off. This is a heavy lift booster. There are no such boosters in the world today. Elon Musk is working on one. Whether he makes one or not, we can make them. We made them a generation ago. They can be made again. 140 tons to low Earth orbit in one launch. Okay? Now, if we had such a system, which is hardly futuristic, how could we do a Mars mission? Well, there we go. This is the mission plan of Mars Direct. You can launch to Mars every 26 months, roughly every 2 years. So here's how it goes. In the first year of the plan, we launch one of these boosters off the Cape, and we use its upper stage to throw to Mars a payload of about 40 tons. If you can lift 140 tons to orbit, you can shoot 40 of that off to Mars. And this is an unmanned payload. It's unwomaned too. There's no one in it at all. It flies out to Mars, takes 8 months to get there on a minimum energy trajectory, and then it uses an aerobrake to capture into Mars orbit. And then after we check it out and check out the weather, we then bring it more deeply into the atmosphere, use the aerobrake to slow us down all the way to subsonic speeds, pop a parachute, come down slow, and put ourselves down softly on Mars with rockets, just like we did with Viking in 1976, or in a somewhat different way with Curiosity in 2012. Now, what is this payload that we have landed on Mars? Okay, it consists of a number of things. The primary object is an Earth return vehicle, which is a little rocket ship for coming back from Mars to Earth. It has a cabin which is 5 meters in diameter with tight quarters for a crew of 4 to take a 6-month voyage from Mars to Earth, but no one's in it now. Then there are 2 methane-oxygen chemical propulsion stages, which, however, are unfueled. They can't be fueled. If they were, this would be much too heavy for a heavy lift booster to shoot off to Mars. But however, in some of the lower stage tanks, we have 6 tons of hydrogen. And then below the vehicle, not shown in this diagram, we have a little truck, like a little pickup truck that runs on a methane-oxygen engine. Okay, and in the back of that truck, we have a little nuclear reactor with a power of 100 kilowatts. Now, 100 kilowatts is about the same amount of power as drives a large car. So we're not talking about a giant nuclear power plant that powers a city. We're just talking about a nice little nuke tucked in the back of a truck. And then we drive the truck a few hundred meters away. We put the reactor on the ground, preferably in a crater, to provide shielding. And then we turn it on. And what we do then is, some basic chemistry in which we react the hydrogen from Mars with, the hydrogen that we brought to Mars with some carbon dioxide, which is what the Martian atmosphere is made of. They turn into methane and water. We electrolyze the water to make oxygen, recycle the hydrogen, and before you know it, we've turned the 6 tons of hydrogen from Earth into 108 tons of methane oxygen on the surface of Mars. Okay, so now we have a fully fueled Earth return vehicle sitting on the surface of Mars. Thank you. Okay, and for those interested, there's the chemistry. By the way, if you want to know more about this, my book, The Case for Mars, is out in English, and it's going to be out in Russian this summer, published by Exmo. Don't miss it. Anyway. Okay. Okay, so the Earth return vehicle is now fueled. So at the next launch window 2 years later, we shoot 2 more rockets off to Mars. The first shoots out another one of these Earth return vehicle systems. The other shoots out a Habitat with a crew of 4 astronauts in it. Now, because our return ride is waiting for us on the surface of Mars, we don't need to fly to Mars in a gigantic Imperial Star Destroyer. We don't even need to fly to Mars in a comparatively modest Millennium Falcon. No, we can fly to Mars in a tuna can. And this is very fortunate because we know how to build tuna cans, although this one is somewhat bigger than the one you find at the supermarket. It is about 8 meters in diameter and 5 meters tall. So it's got 2 decks, each with 2.5 meters of headspace. The upper deck is where the people live. The lower deck is more of a cargo hold workshop kind of place. Here is one potential layout of the upper deck. You see there's a little stateroom for each of the 4 astronauts, a science lab, a galley, exercise area, and in the center is the solar flare storm shelter. Now, this is worth talking about for a second. There's 2 kinds of radiation that can get you in interplanetary space. Solar flares, cosmic rays. They're different. Solar flares come from the sun, a big pulse of radiation, only maybe one big one a year. But in the course of that, it could deliver maybe 10 sieverts of radiation, enough to kill an unshielded astronaut. That would be bad. However, the kind of radiation that solar flares are made of are protons with energies of about 1 million volts, which can be stopped by 12 centimeters of water, or things that from the nuclear point of view are essentially the same thing as water, such as food, or things that water and food become as the mission proceeds. And we have enough of that on board the ship to shield a central area so that if a solar flare happens, you go in there until the all clear rings, you come out, you're safe. Now, the other kind of radiation are cosmic rays. They don't come from the sun, they come from interstellar space. And they have energies, not of millions of volts, but thousands of times that, billions of volts. They would go right through 12 centimeters of water. It would take meters of water to stop them. We can't do that. So you're going to take the dose. You're going to take about half a sievert worth of cosmic rays. But that only represents about a 1% risk of getting cancer at some point later in your life. And in fact, there have been about 10 astronauts and cosmonauts who, staying on the International Space Station or the Mir or the Salyut stations over long durations, have actually gotten that kind of dose, and some in larger cases than they would have gotten going to Mars and back. And we see no radiological casualties among that group at all, okay? These are people we know. But you wouldn't expect that. 0.5% of risk, over 10 people, chances are no one would have encountered a fatality. If you compare that to smoking, which for an average American smoker is about a 20% risk of cancer, they're much better off. So in fact, if you chose the Martian crew out of smokers and you sent them to Mars without their tobacco, you would be reducing their chance of getting cancer. So So one reason to send people to Mars might be for their health. Now, but there is a phenomenon in space which has caused major health effects, and that is zero gravity, which causes the loss of bone and muscle. Now, this is not fatal. It will take us 6 months to get to Mars. That's how long we go on a space station in an average tour. But we don't want the astronauts to get to Mars weak because they have to do field exploration. Hiking around in a spacesuit is like heavy-duty backpacking. The people have to be in shape to do it. They're going to explore. We want them in shape. So we can create artificial gravity by tethering the spacecraft off of the upper stage of the booster that threw them to Mars. That stage is also traveling to Mars, and it can be used as a counterweight on the end of a tether. The tether is about 1,500 meters long. You spin this up at 1 revolution per minute, it will make Mars gravity in the HAB. If you spin it up at a little less than 2 revolutions per minute, it will create Earth gravity in the HAB, and thus there will be no such zero gravity health effects. All right, so it takes 6 months to fly to Mars. And by the way, you want to go to Mars in 6 months because if you don't stop at Mars, if you're on the 6-month trajectory, you will loop around and you will into about twice Earth's distance from the sun and get right back to Earth's distance exactly 2 years after you left. So the Earth will be there. That's called a free return. That's a good safety feature. If you try to go to Mars faster, you loop out further and then you come back. It'll take you longer to get back. There won't be enough, the Earth won't be there. But we get close to Mars, we fire a pyrotechnic, it cuts the cable, we aerobrake into Mars orbit, and then we go and land at landing site number 1, where the fully fueled Earth return vehicle is waiting for us. We should be able to land right there. We've explored the place with robots, we have radar beacons on the ground, we got an ACE flying the HAB, go right there. But if we're off by hundreds of kilometers, we're still okay because we have a pressurized ground rover in the HAB that has a one-way range of 1,000 kilometers. So it would really take really, really bad piloting to land outside of that radius of action. Now, however, if even that happens, if we land over there, excuse me, wrong side of the planet, which would represent a real problem with the pilot selection process at NASA. If that were to happen, we can send the second Earth return vehicle to land near them, and that would be our way home. And finally, if none of that works, we can just tough it out on the surface of Mars until more supplies and another Earth return vehicle can be sent out to us 2 years later. So we have a 4-layer defense in depth on the mission, as well as one abort option. Okay. Now, so we're on Mars. Well, actually, let me talk one more second here. So the second Earth return vehicle, though, is not really for us. It lands somewhere else, where it starts making propellant for the next human mission, which will fly to it 2 years later, along with another Earth return vehicle, which is their backup, but which otherwise opens up landing site number 3. So the plan is every 2 years, 2 boosters launched, 1 to open up a new site, 1 to exploit the previous site. 2 boosters every 2 years is an average of 1 per year. This is something that any nation doing it could certainly afford to do. Now, this is an actual photograph of the Mars base. Okay, so here is the Earth return vehicle, the conical vehicle. There is the reactor and the crater in the background, the tuna can HAB where the astronauts live and work, the exploration rover, some solar panels to use as backup power for the reactor. Also, the engine of the car can be used as backup power. And a greenhouse, which is an experimental system to learn how to grow crops on Mars in Martian soil, Martian gravity, Martian water, Martian sunlight for the benefit of future missions and future bases. Now, we are going to be on Mars for a year and a half before the planets line up to shoot us back on another 6-month voyage home. What are we going to do on Mars in a year and a half? We're going to explore. This actually is a photograph of Mars. taken by the Viking orbiter in 1976. And what you see here are dry riverbeds on Mars, massive numbers of them. Okay, there are no canals on Mars, it's a myth, but there certainly are dry riverbeds, dry oceans, dry lakes, dry ponds. Okay, and Mars had liquid water on it for 1 billion years, 5 times as long as it took life to appear on Earth after there was liquid water here. So if the theory, which by the way was originated by a Russian scientist, Oparin, that life originates from chemistry through a process of complexification of simple chemicals forming more complex chemicals and still more complex until eventually self-reproducing complex systems emerge. If this theory is correct, then life should have appeared on Mars. And if we go to Mars and start doing some serious fossil hunting, we should be able to find some of these fossilized life forms on the surface. And in fact, if we go to Mars and set up drilling rigs and get down to the Martian groundwater, because there is liquid water underground on Mars, which is an environment in which microbial life can survive, we reach that groundwater, we might find survivors of ancient Martian life living there, just as there are survivors of the most ancient life on Earth living in groundwater on Earth, okay, who can no longer survive the surface because of oxygen. We and our friends, the plants, have polluted the Earth's atmosphere with oxygen. But they're still there. They might still be there. We could find them. And if we find them, we'll have proven not just that there's life on Mars, but that life is a general phenomenon in the universe, because there's thousands of planets. We know that now, and they all have, every star has a good distance where you have a habitable zone around it. If life originates everywhere, or if life is a high probability event, it's everywhere. And since the history of life on Earth is one of development from simple forms to more complex forms, manifesting greater capacities for activity, intelligence, and ever more rapid evolution, if life can evolve in this way, it means we're not alone. This is something that thinking men and women have wondered about for thousands of years. So at the end of the mission, we go home. We leave the base behind on Mars. As this plan proceeds, we have a string of exploration bases. But eventually, we'll know the answer to whether there is life on Mars. And the real question is going to be, will there be life on Mars? Mars has the elements needed for life. It means it has the elements needed for civilization. So if we build a base on Mars and start mastering the technologies needed to turn Martian materials into resources, if we learn how to not just make fuel and oxygen on Mars, but to grow plants on Mars, to make ceramics, glasses, metals, plastics, wires, tubes, habitation structures, then Mars becomes a place where human beings can live and where eventually new branches of human civilization can develop. Okay, at the first of many, okay, because Mars is not the final destination, Mars is just the direction. And if we do what we can do in our time, which is establish this first human foothold on Mars, then 500 years from now, there will be new branches of civilization, not just on Mars, but on thousands of planets orbiting stars in this reach of the galaxy. And when they look back at this time, what will they care about? Okay, will they care about who won the various power struggles in various little places? No. But what we did to make their civilization possible is what will matter. This time will be remembered because this is when we first set sail for other worlds. I może być, my możemy делать это вместе. Na Mars.